So this is a story about pi. I think every mathematician is always quite enchanted when they discover that the number pi appears somewhere. Of course, like when we're discussing some geometry or trigonometry, it's not really surprising that pi shows up. But then there are all these instances where pi shows up where a priori there's absolutely no reason why we should expect pi to show up. And that's always very fascinating. And I will be telling you a story about such an incident where pi shows up right now. And it's related to counting so-called up-down permutations. So I should first explain what these are. Let's maybe start with some permutation, just some random permutation, maybe on 4 letters. 1, 2, 3, 4. Of course, we know that there are like 4 factorial permutations of these, but now we will only be interested in those permutations which go up, down, up, down, up, down. So the term up-down permutation, it's also called alternating permutation, is actually pretty self-explanatory. In order to visualize this, it's good to draw such bullets. So I go up, and then I go down, and then I'll go up. And now basically the task to write down an up-down permutation just amounts to filling in the numbers 1, 2, 3, 4 in some order into these bullets. And as I go up in the graphic, this means like the numbers have to go up, and as I go down, the number has to go down. So for example, 1, 2, 3, 4, this is the identity permutation, and it's not an up-down permutation because it goes up, but then it goes up again. So an example for an up-down permutation would be like I start with 1, then I have to go up, so I could go to 4, then I have to go down, so I could go maybe to 2 or to 3. Now the better idea is to go to 2, so I go down, and then I can go up to 3. I could also have messed up, by the way, right? I mean, if instead I had taken the following configuration, I could have started with 1, 4, and then I could have said, okay, I'll go down, I take 3, but then there's nothing I can do anymore because I would have to go up again, but the only number which is left, which would have to go here, is the 2, and then this is not going upwards. So this is it's not possible to complete this. So you see, if you just fill these slots from left to right, it's actually very easy to start with some configuration where it's impossible to actually conclude. Okay, so now we have an interesting question, right? How many up-down permutations are there? On 4 letters, you just see one example here. Is there another one? Do I have to start with the number 1? Certainly not, right? I could maybe start with the number 2 and then go up, 4, then go down again, 1, now I have to go up again, 3, see, that works as well. Different permutation. Good. Now the magic of the whole story is we'll compute the number of these up-down permutations, and we'll call this AN. So let's already define this. So AN is defined as the number of up-down permutations on n letters. Okay, so we'll figure out what this number is for various n, and then the whole magic lies in the following formula. Namely, there is a way to compute pi if only you know these values. So this is a formula. Actually, we'll only be needing the values of up-down permutations on an even number of letters. The whole story, which I will tell you, you can also extend it for the number of up-down permutations on an odd number of letters, but for simplicity, I'll skip this. Good, so what you have to do is you have to compute basically the fraction. So a to n divided by 2n factorial. This is, of course, exactly the fraction how many of the total number of permutations there are on 2n letters. So what percentage of these does have this up-down property? So we're computing this. Okay, and then here in the formula it enters as its inverse. You multiply by 2, and then you take the 2n plus 1th root of this, and then you take the limit of this as n goes to infinity, and that converges to pi. So somehow these up-down configurations are related to pi. And what this video is about is that we will prove this. I will show you a complete proof why this formula holds. But before we start with the theory, it's always good to do some experiments and just explore this a little. Are these numbers a to n, are they big, are they small? Let's have a look. To do this, I actually prepared a little program. It's here, and what this little program does, it just lists, for a given number of letters, it just lists the up-down permutations. Let me not go through what the program really does. It's basically enumerating the permutations, then it checks whether this up-down property holds, and then what it will do is it will print out all the permutations, and it mark those as yellow, which satisfy this up-down property. So let's first maybe do this on just 2 letters. So in this kind of magnitude, we could easily do this by hand still. And you see there is exactly 2 permutations, 2 factorial, as we would expect, and precisely one is an up-down permutation. So no surprises here, right? And maybe on 3 letters, you see, okay, so there are only 2 up-down permutations. Yeah, and maybe let's do a bit more. I mean, so of course, the number n factorial, this grows enormously, right? It's a stronger growth than just exponential growth. So very quickly, it becomes completely inconceivable that you would do this by hand and go through all these permutations and find out which ones have this up-down property. So here for 4 factorial permutations, you see there are just a few are up-down. Let's have a look maybe. So here we have 2, 3, 1, 4, and indeed 2 goes up to 3, goes down to 1, goes up to 4. Whereas for the permutation below, this is 2 goes up to 3, but then it would have to go down again, but it goes to 4, so it's not marked in yellow because it's not an up-down permutation. Yeah, let's maybe have a look at some larger numbers. What about 6 on 6 letters? Now, here you really start to see how sparse these are, right? You can go through large chunks of permutations and then just very sparsely, every now and then, there are a few up-down permutations. And so you see here among all of these, so it turns out there are exactly 61 up-down permutations on 6 letters. But now instead of just listing the up-down permutations, remember we will actually want to compute pi, so we should really look into this counting problem. I have another little program here which does exactly that. So this program will now not list all the permutations and then mark those which are up-down, it will just give us the count. Because this is what really matters for us. So for example, here I'll do this for the first, for all numbers up to 20 letters. Remember, I already told you for simplicity, we will only be considering the case of up-down permutations on even length, on an even number of letters. Maybe some of you recognize these numbers, right? So the count of these up-down permutations is 1, 5, 61, 1385. If you don't recognize these numbers, no worries. We'll understand a lot more about them in a few minutes. Okay, but so you see, even though we'd seen that the number of up-down permutations is a lot smaller than the number of all permutations because they are kind of sparse, you still see that you have a tremendous growth among these numbers. Good. And now let's see how these values actually approach pi. So this is also implemented here. So what this program does now is it will evaluate this expression which I had shown you. So given the count, it will just evaluate this expression here. And then we can see how close this is to pi. And the program marks all those digits which are correct in yellow. And so you see, actually, this is pretty good, right? Because we're gaining a lot of digits here. Actually doing these computation problems, finding out how many such up-down permutations there are, this is a lot of effort because you have to go through all these permutations. So I'm not claiming that this is a good algorithm to determine pi, but at any rate, you see, you're really getting somewhere. So already on 20 letters, you have really a good number of digits right. And let's maybe do a little bit more. We can maybe go up to 80. Then you see this is going well, right? I mean, the number of correct digits is increasing and increasing. By the way, just very quickly to explain why are there some scattered yellow digits here. Well, these digits, they are just correct by accident. This is bound to happen, right? If you just compute some number, it's not the correct number, but the digits are maybe kind of randomly distributed. You would expect that there is a 10% chance that some of the digits are accidentally right. So this explains why there are some scattered yellow dots here. But here you see really what the convergence effect. And so down here, you already see, I mean, I think I'm only outputting, like, what is it, 30 digits? Yeah, so I'm only outputting 30 digits. And you see, like, if I go up to 80 letters, I mean, already before that, all the digits of pi are correct. Yeah, good. So far for the computational stuff. Now it's time to actually understand this theoretically and prove the claim that this really converges to pi. First, we will encode these numbers in some kind of function, and then later we'll discover that this function satisfies a differential equation. And solving this, we can understand what these numbers are. It's amazing. So let's go through this. All of this is due to Désiré André, and it's really a beautiful piece of mathematics. So in order to get started, let's use this graphical depiction which I had for a general up-down permutation. So suppose we have an up-down permutation on n+1 letters. Then I can depict it as follows. So I again draw these bullets. Up again, down again, up again, down again, and so on. Some number of these. And given such an up-down permutation, it just means that I somehow fill these bullets with entries from these n+1 letters. So I can very concretely pick the numbers 1, 2, 3, and so on till n+1. Right, so any such up-down permutation just means that I, in some order, have to fill in these numbers into these bullets so that it goes up, down, up, down, up, down, up, down. Okay, now the first idea one could have is that in one of these slots here, the highest entry must sit. n+1 must sit in one of these slots. And I will call this slot J. And so I should number these slots, and I will do that, but for the numbering of the slots, I'll start with the number 0 actually. So this is slot number 0, this is slot number 1, slot number 2, and so on. And then the last slot will be slot N. So this can be a little bit confusing. Why am I starting to count at 1 for the entries of the permutation, but I'm numbering the slots starting counting from 0. Now, it turns out that this is actually best for the proof. This is the optimal convention for the proof. But it's still a bit weird, right? Because usually we agree on some convention. Either we start counting at 0 or at 1. But here, it's, if you really think about it, not so confusing because we're really talking about two very different objects. These numbers here, these are the entries of the permutation. This is the count of the slot. So even though both are numbers, they really have nothing to do with one another. I mean, I could have used any other letters for this totally ordered set and counting the permutations. It doesn't matter, right? I mean, I could have used, I don't know, A, B, C, D, the alphabet, whatever. But this really just counts the slots. So, right, this is really the 0th, 1st, 2nd, and so on slot. So two different things. Okay, good. Now, the observation is, in one of these slots, we'll have the entry n+1 because it's a permutation, right? There will be exactly one such slot. And the next realization is that it can only sit in one of these slots up here, not in one of the lower slots. So maybe let's say n+1 sits here. And I will call the slot where that happens J. So let me quickly prove why can it only sit in one of the upper slots. And for this to be completely accurate, actually, and we need to assume that our n is at least 1. So it means that we'll consider only up-down permutations on at least 2 letters. This kind of makes sense because if you have only 1 letter, how will you tell whether this goes up-down at all? Well, you have nothing to compare it to. Okay, so we consider only up-down permutations on at least 2 letters. And this means if n+1 were in one of these lower entries, it means that you can go at least to the left or to the right. I mean, if there are 2 letters, then there must be a neighboring one, either to the left or to the right, maybe to both directions. But whatever, because this is a down slot, it means that this you will have to go up, or here you would have to go up, but that's impossible if your value here is n+1, because there's nothing you can further go up. Okay, so this proves n+1 must sit in one of these upper slots, which actually in terms of our numbering of the slots means that we know that J is odd, right? So I mean, the first slot would have been 1, and then the next slot, which is up here, is 3, 5, and so on. Good. Now the idea is that we subdivide the set of all up-down permutations according to what the number J is, right? According to where the entry n+1 sits. So I consider the set of all, so this is the set of all up-down permutations on n+1 letters. And again, for safety reasons, I'll impose that at least 2 letters. And now I learn that I can write this as a disjoint union. This will be my symbol for a disjoint union, according to the indexing of J. And this can go from 0 to n, right? From 0 to n. But it can only be odd according to where the entry n plus 1 sits. So this is now the subset of all up-down permutations on n plus 1 letters with n plus 1 in the jth slot. Okay, so I have this set of all up-down permutations, and now I've subdivided it in a disjoint decomposition in sets according to where this highest entry n plus 1 sits. Good. And now the next thing I can do is I can have a look at what are actually, if I go to the left of this, what are the entries here? And if the n plus 1 is in the jth slot, you can actually observe that the number of slots which occur to the left are exactly j many. This is actually the reason why we chose the indexing of j to begin with 0, so that we have this very nice formula for counting the slots, right? So, I mean, had n plus 1 be sitting here in slot 1, there would be exactly 1 slot to the left. Now it sits here in the 3rd slot, and indeed there are just 3 slots to the left. So in general, wherever n plus 1 sits, there will be j slots to the left, and then there will be some numbers in there. And we can now further subdivide the set of all up-down permutations according to what the numbers are which are sitting in here. So what can they possibly be? Well, it's a j element subset of all the numbers in here except for n plus 1, because n plus 1 cannot be here because it's a permutation and it already sits here. Good. So I further want to subdivide this, and I can just write this down as a map. So I map this down to an even better disjoint decomposition. So I'm still keeping my disjoint decomposition according to where the top entry sits. We already had this. But now I also run over all the subsets S with exactly j elements. And such that S is a subset of 1, 2, 3, and so on till n. Let me again repeat why I do that. This set S will be the set of elements which are here to the left, and because n plus 1 is already taken, this must be a subset, a j element subset of these numbers. Good. So this is this, and then the set, of course, which I write here. Now, this is a bit complicated, but so this is the set of all up-down permutations. I'll shorten this a bit. On n plus 1 letters with n plus 1 in jth slot. Yeah, sorry, it's a bit lengthy. And so to the left of jth slot, entries come from S. Very complicated, but well. So now I'm starting from this decomposition according to where the top entry is. I'll now further decompose it according to what elements sit in here. Good. And now comes the crucial idea for the recursion. Actually, if you chop this part off, if you just delete this part of the up-down permutation, you know that the remaining bit is also an up-down permutation, right? Because this goes up-down. And this would have, I mean, even if n plus 1, for example, were here, again, up, down, up, down. So if you just keep all the stuff to the left of the top entry, this is an up-down permutation. Now, not on this whole set up here, but on what set? Well, the set which we just called S, because S was the set of the entries which are to the left. But you can also chop up this thing in the other direction. So remove anything which is n plus 1 and before. And then again, this is an up-down permutation, right? I mean, n plus 1 is up. So again, down here. And so it goes up, down, up, down. So again, this will also be an up-down permutation. Cool. So now this is what gets the recursion going. We will just start with this permutation, and then we just can map it to an up-down permutation on the subset S, and an up-down permutation on the remaining letters. But it's easy to say what these are, because they are from 1 going till n minus the set S, because the elements which are to the left are in S and it's a permutation, so all the other elements must live on this side. Okay, cool. So we get a further map from this set down to an up-down permutation on now J letters, right? Just these on the J letters S, and we don't really know much more about this. So this is what we chop off on the left, and here an up-down permutation on the, so how many are these? So these are n+1 letters, and then we remove J letters, and we also remove n+1 because we're chopping that off as well. So this is on the n+1 minus J+1, right? So yeah, J+1, right? So n+1 letters in total, remove J, and then this one as well. So that's J+1, which have to be removed. On the n+1 minus J+1 letters. And these are from 1 to 3 and so on, going to n without S. They're just the remaining letters. I mean, so this is a map from this set up here down to these. But the key point is actually this map here. This is entry-wise for every term in this disjoint union. This is actually a bijection. So I claim that this thing, this map here, is a bijection. Yeah, it identifies this big thing here with this thing down here. So why is that? Well, because I can just revert the procedure which I've just explained. So I could either start with this permutation where I've fixed where the top entry is and I've fixed what elements go to the left, and then I chop off this, I get this, and I chop off here, and I get these two permutations. So this was the map down here. But also in reverse, if I have an up-down permutation on these letters S, which is a subset of 1, 2, 3, n, then I can just start writing them. It's an up-down permutation, so I get that much of an up-down permutation. Then I just place n+1. So I need to check, is this actually an up-down permutation? So I need to check at this point, does this go up? But it definitely has to go up, because the set S was taken from 1 till n, and n+1 is bigger than all of these. So this can really only be an up. Okay, so now I have an up-down permutation established up to here. And then now I just glue this up-down permutation to the right. Okay, so this is an up-down permutation, so I get this up-down pattern. That's fine. I need to check that this really goes down here at this point where I glue it, but this is also no problem because just as before, n+1 is the highest entry, so whatever entry comes here, it has to be smaller, so that works. And now I just have to make sure that all in all, as when I glued this together, that all the entries which are in here come from this set, but this is also fine because the letters which I had in here, they are from going from 1 till n, then I have n+1, and then here I have exactly the remaining letters to complete that to this set. So this establishes that this map actually is a bijection. Good. And then the thing is, this map here, up here, this was also a bijection. I mean, this was just a further decomposition of all these according to what the set S is. Yeah, maybe I should be more careful here, not that you think that this belongs to this. So I can also write, I mean, I can copy this disjoint union here. Right, so this was a bijection from this set to this down here. Yeah, not including these disjoint union. Okay, so, but I can write this here. Now, after all these elaborations, the key point is that we want to count these sets to get a recursion about the number of up-down permutations, and this is very easy now, because what we have deduced from this is that if I take the count of all up-down permutations on n+1 letters, remember this was the number a n+1, then this is the same as, okay, so here I have a disjoint decomposition, so that means the number of elements is just the sum, so I get a sum. This is indexed over j from 0 to n with j odd, Okay, and then I had another, so I could identify this with this. So then I had another sum. Again, this was also disjoint. And this is indexed over all j element subsets of this set. So I pick a j element subset of an n element set. So we know that the number of that is n over j, binomial coefficient. Okay, and then for every such choice, down here I'm using this bijection, I had an up-down permutation on the j letters in S. Note that actually it's completely irrelevant how we name these letters, whether they are 1, 2, 3, 4, n, or A, B, C, D, or 1, 27, 855 or so. The number of up-down permutations only depends on the underlying totally ordered set, as there is a canonical one. It only depends on the underlying cardinality. So this will just be the number of up-down permutations on j letters. So this is aj, right? And this is the number of up-down permutations on the remaining number of letters. So let me just quickly check that n plus 1 minus j plus 1 minus 1. So plus 1 minus 1 cancels this. So this is actually n minus j. Good. So this is a n minus j. Yeah, and so to be completely precise, remember that we had assumed that n is at least 1, so I should only formulate this identity for n at least 1. And this is the key identity. Yeah, this is the key recursion. This allows you to count the number of up-down permutations on the basis of knowing the number of these up-down permutations for a smaller number of letters. Note that j only ranges from 0 to n, so you'll never get up as high as n plus 1 in any of these terms. Yeah, very cool. Now, in order to proceed, we have to do a little bit of a trick. And the thing is, we've just counted up-down permutations, but you could also count down-up permutations. So let me quickly discuss this. So maybe I'll do this on a new piece of paper. So let Bn be the number of down-up permutations on n letters. And you can guess, I mean, I probably don't have to define this carefully. It just means instead of going up, down, it just means you consider permutations which go down and then up, down, and then up, down, and then, and so on. Now, the cool thing about it is you can analyze them in exactly the same fashion as before. So again, you can have a look at, also let's actually do this for n plus 1. So you can just distinguish them according to where the highest letter n plus 1 sits. Note that this time things are a little bit different. This time the index of this will have to be even, right? So again, I index the slots, 1, 2, and so on till n. And because n plus 1 again must sit up here, just because by the same argument as before that the neighboring entries must be lower if this is the top entry. But you see, this time this means that the n plus 1 will sit in an even index. And then you can run exactly the same argument as before, and you get basically the same formula. You get the formula that Bn plus 1 is the same as the number j from 0 to n, this time j even, right? Because we've observed that the highest entry must sit in an even slot, of n over j bj times bn minus j. Also at least n at least 1. Exactly the same formula, right? This is exactly the same formula. The only difference is that now the top entry sits in an even slot instead of an odd slot. The rest of the formula is exactly the same. And the proof is also completely the same, because again, you just chop off the down-up permutation. If you just look at what happens to the left, yeah, again, this is a down-up permutation. If you just look at what happens to the right, again, this is a, oh, sorry, so this is an up-down permutation. So on the right, this is an minus j. Yeah, okay, good. So very similar formula. Now, okay, so what's this confusion here with the letters A and B? Now, the thing is, actually, A and B are the same. This is the next claim. The number of up-down permutations is exactly the same as the number of down-up permutations. And the reason for this is very simple. If you have any up-down permutation on these n letters, so these letters are 1, 2, 3, and so on till n, but what you can just do is you can just map this set to the set n, n minus 1, and so on. You just reverse the order. Yeah? You can always do that. But so if you have an up-down permutation and you just, whatever the numbers in there are, you replace them by these, then because this is order reversing, this will just revert all the up-down relations and turning an up-down permutation into a down-up permutation. And this is a bijection, so you can also turn any down-up permutation into an up-down permutation. So just using this simple little trick, you know that the numbers of up-down permutations are actually the same as down-up permutations. Good. So what was the whole thing with writing all this down? What was that good for if this is the same count anyway? Well, what it is good for is that it now allows us to write down a formula where we do not have this somewhat perhaps disturbing, as we'll see, this would be disturbing, as this restriction to j odd, or here j even. Namely, what I can do is I will just sum these two formulas. So an plus 1 plus bn plus 1. So this is the number of up-down permutations plus the number of down-up permutations. Now I had a formula for the number of up-down permutations, this one. So this is the sum j from 0 to n of j odd of n over j, aj, an minus j. Okay, and now I have to add the terms coming from the down-up permutations. And for this I had a formula as well. This was this one. Okay, so this is the sum, j from 0 to, now j even, to n, of n over j of bj times an minus j. Good. And now I use this observation that an and bn is actually the same. So really on the left-hand side, I get just twice the number of up-down permutations on n plus 1 letters. And here I get, well, you know, the thing is I can now just combine these sums, right? Because this b I can replace by an a because a is the same as b. And then the summands are precisely the same, right? This is just n over j in both instances. And then I have aj, right? bj is the same as aj. And then an minus j and an minus j here. So exactly the same terms. But these summands they are for j odd. These are for j even. Well, so if I combine the sums, it means I'm just summing over all j. Right? So now I just have the sum from 0 to n of n over j, aj times an minus j. And now I will never ever again in this proof need the number of down-up permutations, right? This we will now return to our up-down permutations. So this consideration of the down-up permutations, this was just a little tiny detour to develop this formula. And let me also tell you at this point, it's actually possible to do all that I will be doing. You can actually also do this with this formula, but the next steps in the proof get a little bit more complicated if you use this formula. Now we had this little detour with the down-up permutations, which maybe seemed a little bit weird, but it turns out that using this formula, which now took this little detour, the rest of the proof is simpler. So this is the formula we will be using. And that's precisely because we got rid of this j odd condition in the index. Cool. So maybe let's just think about what we have established so far. So we want to count the number of up-down permutations, and we've developed a very nice recursion formula allowing us to compute the number of up-down permutations on one more letter if we know the numbers of all these for a smaller number of letters. I mean, this is nice for computation, right? We could write a little computer program now computing all these values on the basis of this. So this is nice. It's certainly much better than really counting the permutations, right? Going through all the permutations and then just checking whether the up-down condition holds. So that's good. So we've really made an advance here, but we're still far away from seeing what this has to do with pi. And for this, we need this next ingenious idea. And that is the idea that this term here looks a little bit like a term you find when you play around with the exponential series. I don't know whether you've ever done this, but of course the exponential function has this power series. E to the x is the sum n from 0 to infinity, x to the n divided by n factorial. And now you can check out what happens when you multiply this series with itself. And of course, you know, e to the x times e to the y, this is the same as e to the x plus y. So somehow when you just plug in these sums here, so you get a sum here on the left, the summons and the sum here. So when you expand the sum, you somehow should get this term. And if you do this, I will not do this now, but if you do this, you will discover that there are terms which look a lot like this. And so inspired by this, the idea of André was that you just work with a modified exponential series, not this one, but the one where you build in these numbers an. So let's do this. So what André did is he defined a function, f of z. And the definition of the function, it's just, it goes from 0 to infinity, and it's just an times z to the n divided by n factorial, right? So if an was always 1, this would just be the ordinary exponential function. But now what I put in here are these numbers of up-down permutations. And now to see what this has to do with our little beautiful recursion formula here, all you have to do is you have to square this. So let's do this. This is the analog of this product of exponential functions, right? You can also do this with ex times ex. Good. So let me square this. So this is fz squared is the same as the sum from 0 to infinity of, well, and I can directly introduce a second index. Same thing for the factors, for the summons coming from the second factor, and then it's like an times am z to the n divided by n factorial z to the m divided by m factorial. Okay, and now I'll rearrange this according to what powers of z occur, because this is really the power z to the n plus m. So I'll just write this as a sum n from 0 to infinity, and now with j, a new index j going from 0 to n. And now I'll be replacing the index m by the index n minus j. So this is, now I will give this a different name, p. P will now be n plus m. And j will be ranging for all the choices of what previously m could be, so that n plus m add up to p. So I get aj multiplied with a, so this is then also p, p minus j times z to the j divided by j factorial times z to the p minus j divided by p minus j factorial. Yeah, okay, and now this is the same as the sum from 0 to infinity of the sum j going from 0 to p of aj times a p minus j. Now z to the j times z to the p minus j, of course, is z to the p. I will actually write this outside of the sum, z to the p. And then here I have 1 divided by j factorial times p minus j factorial. And you clearly recognize that I might bring this in the shape of a binomial coefficient if only I had p factorial written here. So I can introduce p factorial here and then divide by p factorial here to compensate for having introduced this new thing. And then I get a binomial coefficient here. I will do this. This is looking good, because then I have a product of these values a with a binomial coefficient. Now at this point, maybe I should really switch back the name of p to n. I just didn't want to do this here because I had already used n up here. But so let me rewrite this. So p now becomes n. So I go from 0 to infinity. Now I have the sum j from 0 to n. And then aj a n minus j. And then here I can write the binomial coefficient when multiplying with n factorial. So this is n over j. And then here I have times z to the n divided by n factorial. Okay, and now that's basically it, right? Because you recognize that this thing is pretty much this, right? This is the same term, right? You have, right, I mean, here you have the binomial coefficient to the right, and here it's to the left, but this is the same term. But this is 2an plus 1. So this means in here I can replace this inner sum by 2an plus 1. I have to be a tiny little bit careful because really I only prove this formula under the assumption that n is at least 1. Remember, we had assumed this earlier on. So this is only really valid for n at least 1. So I need to be a little bit careful because here n can also be 0. So let me actually consider the summand where n is 0 separately. So I will now just be writing down the summand where n is 0, and then I'll just consider the rest of the sum. So for n is 0, the sum only ranges from 0 to 0, and then I have a0 times a0 times 0 over 0 times z to the 0 over n factorial. Okay, so I just get this term. Okay, and now I need the rest of the sum where n is at least 1. But when n is at least 1, I can use this formula. And I can rewrite this term here as this sum 2an plus 1. So I get the sum from n from 1 to infinity of 2an plus 1 times z to the n divided by n factorial. So I hope you see somehow now the magic of why it was useful to encode all these counting numbers of up-down permutations inside of this function, because we get a funny identity for the square of the function. I mean, we really got a massive simplification in here just using this. And the idea is that this term here actually looks a lot like the derivative of f. I should explain this, but so in general, if you work with such expressions, you will know that an index shift in the summands usually corresponds to taking a derivative. Let me do this as an extra computation. Let's just take the derivative of this function. Yeah, so f derivative. I can just do a term-wise differentiation. I've never really carefully thought about the convergence of this. For the moment, you can just treat this as formal power series, so you don't have to worry about convergence. Okay, so I do term-wise differentiation. So this sum is from 0 to infinity, and then I have a n, and then I get n to the z to the n minus 1 over n factorial. Okay, the summand n equals to 0 is actually irrelevant because I multiply with 0, so it disappears. So really this is a sum starting from 1 to infinity of a n times, okay, and n divided by n factorial. This is just z to the n minus 1 divided by n minus 1 factorial. Okay, and now I can re-index the sum. Instead of starting counting at 1, I can re-index it so that I start summing for n equals to 0, and then I have to replace every n by n plus 1 here so that it's still the same sum. So this is the same as the sum from 0 to infinity of a n plus 1, right? Because the first summand must be a1. So this is true now. And then z to the n divided by n factorial. Okay, now you see exactly this phenomenon which I had just described verbally. I consider the derivative of this function, and it just amounts to a shift of the indices in this sequence of up-down permutation counts by n plus 1. And now look at how closely this resembles the expression I have up here, right? This is really stunning. So here I have a n plus 1 zn divided by n factorial, and here I have a n plus 1 zn divided by n factorial. Very close. Good. Now, the next steps will be figuring out what this is. This is very tempting now. We almost have an identity between the square of the function and the derivative, but one has to be a little bit careful here because of all the little details in this thing here. So let's just first work out what this thing here is. So what's a0? So I haven't really talked about this so far. An was defined as the number of up-down permutations, but what does that mean when the n is 0? Remember, when we consider up-down permutations, they go up, down, up, down, up, down. And we had this identity, right? So 2an plus 1 is the same as the sum n over j of aj times an minus j for n at least 1. So we had somehow located this entry n plus 1 up here. I had kind of tacitly in our proof assumed that this n plus 1 sits somewhere in the middle so that you always have a nice way of thinking about what the truncation or chopping of the left part or chopping of the right part is. But let's just look at an extreme case. So j equals to 0 actually with an up-down permutation cannot happen, but it could be here, right? So n plus 1 actually can only be here. So here this no fringe case occurs, right? For an up-down permutation on this number of slots. But of course, an up-down permutation doesn't have to end on a down term, right? It could be shorter. So let's just imagine this thing is not here. And then this could really happen, right? The highest entry is all to the right. Now, what should my counting formula give me when I chop this into two up-down permutations? Well, I get the usual count to the left, but how many permutations should I count to the right? Well, precisely one, right? Because only the number of permutations to the left counts. There's nothing to the right. So this tells me that in this fringe case, when so this would be slot 0, 1, and then the last slot is slot n. So if when j is the same as n, then I would really get here a n minus n, so really a 0, a naught, and this should really be 1. So I learned that this formula in this case only works if I agree on the convention that a naught is 1. And I can also see the same thing when the top entry sits in the first bits. Now this cannot happen for an up-down permutation, but it can happen for a down-up permutation. Right, this is a down-up permutation. Here it could happen that n plus 1 sits in the leftmost slot. So this would be slot 0. But again, if I do now this chopping construction, so I try to divide the set of all down-up permutations in down-up permutations to the left and up-down permutations on the right. Again, there's no variation possible in the left bit, so this should just count as 1. So I really see, actually, in order to give this formula meaning, also in the fringe case where j is 0, this is the convention. And now, with this insight, I can also figure out what this is, right? So a naught was 1, so this is 1 times 1, and this is also 1. So really what I get here is this is 1 plus, and then the sum from 1 to infinity of 2a n plus 1 zn divided by n factorial. Good. Now there is another little problem, and that's the problem that when I compute the derivative, the sum actually starts at 0. So it's almost the thing I have here. Very much almost, but not quite, because here I start summing at 1. So what I do is I will just start summing at, I'll just start the sum at 0 here as well, and then I'll just subtract what I kind of over added to the formula. Yeah, so let me just fix this by just, I don't know, not fix, but let me just adapt this so that I start counting here also at 0. Okay, so what did I now additionally add? Well, I added a new summand, and this summand is 2 times a1 times nothing. So I just added 2 times a1. So I just have to subtract this so that the formula is correct again. Right now, so now I've added the summand here, and I have to subtract this. So what's the number of up-down permutations on exactly one letter? Well, this is just, I mean, since there is no up-down or down-up, if there's just one letter, this is just the amount of permutations on one letter. So this is 1. So this total thing is 2. So really I have 1 minus 2 and this term was the same as the derivative of f. So I get the derivative of f, plus 1 minus 2, so this is minus 1. So I've deduced a new beautiful thing, and this is that fz squared is the same as the derivative of f minus 1. Oh, except for I've made a tiny little mistake, and this is that there was 2an, right? So here we had just an plus 1, and here I have 2an plus 1. So I actually need to multiply this by 2. So I get 2 times the derivative minus 1. Again, let me maybe summarize what we've done. So as the first step, we've considered a model for how we can count up-down permutations, which gave us a formula, a recursion formula. Now we're writing down these coefficients, these counts for how many up-down permutations are. We're making them coefficients in a function, so that when we square this function, this recursion naturally shows up in the middle of this computation when we expand this square. And using that, we discovered that this function satisfies this differential equation. So now the next ingenious trick, and this is like, so André had this idea and he did all of this. This is really amazing. Now the next idea is, hey, we could try to solve this differential equation. And if we do that, then we know what f is, and then maybe we can determine what the expansion coefficients of f are in a different way. And well, they are just our numbers an. And this is exactly what we'll do. And this will give us a connection between the numbers an to pi. Cool. So the next thing we have to do is we have to solve this differential equation. This is so cool, like in maths, when different techniques mix, right? So I'll just call the function f, I'll just call it y, okay? And then this differential equation here, I can rewrite this as follows. So this is y squared is the same as 2 times dy after dz. So my variable is called z minus 1. Okay, let's figure that out. So this is the same as, so plus 1. So this means 2 times, sorry, I'll have to do this step by step. So 2 times dy to dz are the same as y squared plus 1. Okay, so dy over dz is the same as y squared plus 1 over 2. Okay, and now I use this separation of variables technique to solve the differential equation. So this means that dz over dy is actually the same as twice 1 divided by 1 plus y squared. And now I integrate. This means z is the same as the integral of 1 over 1 plus y squared plus some constant of integration, right? dy. Always you have to be careful about this constant of integration, which at the moment we don't know, but which we can always determine later using boundary conditions. Now here I recognize that this is the arcus-tangent function. So this is arcus-tangent of y. Let's just double check that that's really true. You can skip ahead if you find this obvious. But so, right, the tangent of t is the same as sine of t divided by cosine of t. So the derivative of the tangent function is the same by the quotient rule as derivative of sine is cosine of t times the cosine of t minus, now derivative of the cosine is minus sine t multiplied with sine of t divided by the denominator squared. So this is cosine squared t. So this is the same as, so this is cosine squared, this is cosine squared. So this is 1 plus sine squared divided by cosine squared. So this is sine squared t divided by cosine squared t. This is the same as 1 plus the tangent of t squared. So this means if I define the function g t as the tangent of t, then dg to the dt is, just by this computation, the same as 1 plus g squared. So inverting this means that dt over dg is the same as 1 plus 1 over g squared. Okay, and that's it, right? Because this is exactly what we had to integrate up here, right? This was 1 divided by 1 plus y squared. Here I have 1, okay, it's called g now, but so this shows that the integrating these functions gives the inverse of the tangent function, which is the arcus-tangent function. Okay, so that fits. Okay, cool. So let's continue here. So I know that z is the same as twice the arcus-tangent function of y plus so far unknown constant of integration. Okay, good. Of course, our function was y, right? I just for the purpose of this solving the differential equation, I had briefly allowed myself to rename f as y. We need to figure out what f is, right? This was what we wanted to do, so we have to solve this for y. So I see that's twice z minus z minus c. I get z minus c, and is twice the arcus tangent. So, oh, sorry, this is wrong. This is divided by 2 is the same as the arcus tangent of y. And now applying the tangent function, I get that y is the same as the tangent of z divided by 2 minus c divided by 2. I will just call this c tilde. I mean, this is some constant. We don't yet know what the value is, but I can just rename c divided by 2 as being c tilde. Okay, so now we've learned another beautiful thing, because now we know something about our function y. Y was the same as f, remember that. Yeah, so we already have figured out that if we expand this function around the origin, then for the correct constant of integration, then the coefficients in the expansion will be the counts of the up-down permutations. Awesome. Good. So what is this c tilde? Well, this is not so difficult to figure out, because let's just plug in z equal to 0, right? So this is y was depending on z. So I learned that y of 0, which is the same as f of 0, is the same as the tangent of, well, let's just make this a plus then, right? I mean, I can also replace the constant by minus the constant, or the constant. So then it's just the tangent of c tilde. F was this. I plug in 0 for z. This just kills all the higher coefficients. Only the coefficient for n equals to 0 remains, where I have a naught. A naught was 1. So I learned that this is actually 1. Okay, so now this is easy enough. So I'm asking for what is the value c tilde so that the tangent is 1. And this means it's 45 degrees, right? So for 45 degrees, I have precisely that the ratio of these two sides of the triangle is precisely 1, right? So this is pi divided by 2. Pi divided by 2 is 90 degrees, so this is pi divided by 4. So we deduce c tilde is pi divided by 4. Okay, so new formula. Now I know that f of z is the same as the tangent function of z divided by 2 plus pi divided by 4. We're slowly getting somewhere. And also note that, I mean, of course, we wanted to produce a relation to the number pi, and note how magically we've suddenly arrived somewhere in the proximity of trigonometry, and the number pi is already appearing somewhere. So it's not so surprising anymore that there might be such a connection. We need to rewrite this a little bit, and for this I will use a half angle formula, right? Because this is the tangent of, I can rewrite this as 1 over 2 times z plus pi divided by 2, right? This is a tangent of a half angle. So I could now look up this formula, but usually one can also do this by hand. So for all these formulas with a half angle formulas with a tangent, it's always the same thing you have to draw. It's always this thing. So you draw a unit circle. Let's see how well I can do this. Well, wherever. And then for a certain angle, so the angle will be this. Yeah, so the angle will be z plus pi divided by 2. So the idea to find these half angle formulas is that you always consider this other triangle, namely this triangle you get when you connect this point to this point here. And the reason for that is that you just need to study what this angle here is. Now, because this is a unit circle, we know that the length of this line here is 1 and the length of this line is 1. So this is an isosceles triangle. Both of these sides have the same length. So this means that the angle here must also be beta, whatever this is. But now you can figure out what the angle is, right? Because this thing down here, this is just 180 degrees minus alpha. So I know that the sum of the angles in a triangle is 180 degrees. So this is pi is equal to beta plus 180 degrees minus alpha. So this is pi minus alpha. So this is pi is the same as twice beta plus pi minus alpha. I cancel pi, so I get that alpha is the same as 2 times beta, so I deduce that beta is exactly alpha divided by 2. And this is the reason why this construction is good for half-angle formulas, because it always turns out that this angle here is exactly half the angle. So using this triangle, you figure out the half-angle formulas. Good. So now this is the first angle computation here. And now for the rest of the computation, let's quickly remember what the sides of this triangle are. So this is the angle alpha. So this means that this thing up here, this will be sine of alpha, and this will be cosine of alpha. So you see how you can find these trigonometric identities in this little figure. Now the next angle we need to compute is this one up here. Let's call it maybe gamma. This is also easy to compute, right? Because this is a right angle triangle. So I know that 180 degrees is the same as alpha plus gamma plus 90 degrees, which is pi divided by 2. So from this I can deduce what gamma is. Gamma is the same as, now let me not make a mistake, it's pi minus pi divided by 2 minus alpha. So this is the same as pi divided by 2 minus alpha. So, okay, so now I know what gamma is. That was easy enough. And now we can actually look at the triangle, which is really relevant for our considerations. And this is this one here. Now what's the angle here? Well, the point is, of course, that this total angle here, this must be 90 degrees, right? Because I'm having a unit circle. I have these 2 points here, and I'm just drawing the triangle to a point on the unit circle. So we know that this total angle here must be 90 degrees. So I can compute this angle because I know these two. Yeah. So this angle up here, let's call it epsilon. And not that it would have to be very small, but it's that. So epsilon is 90 degrees minus beta minus gamma. I'm having the feeling maybe I'm doing this in a too complicated fashion, but now I'll just plug in these formulas. I mean, now we are basically there. So beta is alpha divided by 2, so this is minus alpha divided by 2. And gamma is pi divided by 2 minus alpha. So this is pi divided by 2 minus alpha divided by 2 minus pi divided by 2 plus alpha. Pi divided by 2 cancels against this, and then I have alpha minus half alpha, so this is alpha divided by 2. Okay, good. So epsilon is actually alpha divided by 2. So note that again we found an angle in this little picture which is precisely half the angle of this. Yeah, and there surely is a slicker way to do this, except not using all these dull computations down here. Anyway, so we found another triangle here which has precisely half the angle. And that's the triangle we need for figuring out what the tangent is, because the tangent now of alpha divided by 2 just from this picture is this side here, which, because this is a unit circle, is precisely 1 minus the cosine of alpha, 1 minus the cosine of alpha, divided by this side, which is just the sine of alpha. So this is this. Okay, and yeah, I could just have looked this half angle formula up, but now we've, I mean, we didn't have anything else to do in this computation, so why not that? Okay, and now we're using this formula here. So let me copy that in order not to get completely confused. So f of z is the same as the tangent of 1/2 of z plus pi divided by 2. And now this is, now I use this formula up here. So this is the same as, so alpha is plus pi divided by 2. So I know that this is now the same as 1 minus the cosine of z plus pi divided by 2. and divided by the sine of z of pi, z plus pi divided by 2. Yeah, there you go. So why are we doing this? Well, so now we have the sine and the cosine and they're just shifted. That's maybe a useful thing. Let's just remember that the sine looks something like this, right? So here's 2 pi, and the cosine looks something like this. So you see, so pi is here, so pi divided by 2 is here. So you see actually the shift we're using here, this is exactly the shift which basically replaces a sine by a cosine. So this is the same 1 minus, okay, now I have to get the sign right. So if I shift the cosine by plus pi divided by 2, so the shifting with the plus means I'm shifting to the left. So I'm actually getting down here. So this means I'm getting minus sinus of z. Okay. And then now down here I have the sine function. The sine function is this function. So again, I also shift this. And then I'm just getting, this point here just moves to the left. And I'm just recognizing the ordinary cosine function then. So this is then divided by cosine of z. Okay, so I get just 1 plus sinus of z divided by cosine of z or z, whichever you prefer. Okay, and this is the same as 1 divided by cosine of z plus sinus of z divided by cosine of z, which is just the tangent of z. And there you go. We've just shown all in all that f of z is the same as 1 divided by cosine of z plus the tangent of z. That was quite some work. Good. Now there's another trick. Remember the idea behind this was that we had encoded in our function f our numbers of up-down permutations, right? This was here, right? F was this function where the number of up-down permutations is the coefficient. So this means now we have to extract the coefficients of these power series expansions for these functions to figure out what these numbers are. Well, this is maybe not so easy, but there is a dramatic simplification. Namely, I already told you that for the purposes of this video, let's just look at the number of up-down permutations on an even number of letters. This is not something I could have done all along, because in this recursion formulas at the beginning, we always, when we chop off some up-down permutation of even length, the chopped up pieces, they can easily have odd length. So it wouldn't have worked to do the simplification all along, but now we do it. And this does something beautiful to this expression, because it means that we are only interested in the coefficients here for even n, right? So we're only interested now in the coefficients for even n. So this means we're interested in the coefficients of the even powers in the power series expansion. However, recall that the tangent is an odd function, right? The tangent looks something like this, and then this repeats, right? So this is an odd function, and the cosine, however, this is an even function. But we also know that the power series expansion of an odd function has only non-zero coefficients, can only be at odd powers of z, and for an even function can only be at even powers of z. So this means that actually, if we're only interested in the coefficients for n even, they are entirely coming from this term here, because this is an even function. And this term doesn't change them, it doesn't affect them at all, because it's an odd function, so this will only have a contribution to the odd indexed powers of z. So we deduce from this that a to n is the same as the 2nth power series coefficient when you expand around the origin of the function 1 divided by cosine of z. And we can completely discard this tangent term. Nobody cares. It's okay if we are only interested in the even indexed terms. So this is some magic, beautiful trick. And now for the rest of the video, I will only be considering these up-down permutations on even numbers of letters, but the theory can also be completely developed in the case of odd numbers of letters. There's no problem. All you have to do is, instead of analyzing this function, you have to analyze this function, which I will not do here, but you can do it. Okay, cool. So all we have to understand is the function 1 divided by cosine. Right? So 1 divided by cosine of z is an even function. So in its power series expansion, it will have only even coefficients. And as we've just deduced, these are exactly where the numbers we're interested in. So these are a to n, z to the 2n divided by 2n. Yeah, so now the big question is, of course, what do we actually learn? How can we now connect this to pi? Because remember, this was what we have to do, right? We wanted to prove that there is a limit formula computing pi on the basis of these numbers. So somehow this needs to be connected to pi. Now let me first show you an easy way to do this. The easy way is that we could consider the radius of convergence of this series. And what is that? Well, again, let me just draw the graph of the cosine. Looks something like this. Now the point is, of course, that when you have a function like this is analytic, right? A cosine of 0 is 1. So this is an analytic function, a holomorphic function in the neighborhood of 0. And you know by complex analysis that the radius of convergence of this series is determined by where this function, this meromorphic function, where it hits the first pole. And the pole of this will of course be exactly where the function cosine has a 0, but we to understand perfectly, even in the complex plane where the zeros of the cosine are, they are on the real axis and they are here, right? So this is like, here you have 2 pi, here you have pi, and here you have pi divided by 2, and here minus pi divided by 2, right? So this is the location of the first zeros of the cosine as you progress on circles around on the origin. These are the first zeros you hit, and so these are also the first poles you hit as you're expanding from the origin in bigger and bigger circles around the origin. So this means they are the obstruction to the radius of convergence. So this means the radius of convergence of this formula will be, of this power series expansion, will be pi divided by 2. Okay, and now there's this famous Cauchy-Hadamard formula for the radius of convergence. And this formula tells you that 1 divided by the radius of convergence is the same as the lim sub, n going to infinity, of the corresponding roots of the terms in the power series. So this is the lim sub of a to n divided by 2n factorial. And then you have to take the 1 over 2nth root. So usually in the Cauchy-Hadamard formula, you have to go over all of the coefficients, and then you just have you take the nth root. But in our formula up here, we only have all the coefficients at odd indices. They are 0, so they don't actually contribute to the lim sub. So I can just remove them, but then we have to keep in mind that these even indexed terms, that they occur at even indices. So when you take the nth root for the nth coefficient, we also have to use the even indices here. Okay, so, and I just told you already from this graphic that the radius of convergence of this is pi divided by 2, because these are closest poles to the origin. So this is 1 divided by pi divided by 2. Okay, and now you see where I'm getting at. There's suddenly a relationship between pi and the fraction of the up-down permutations divided by the number of all permutations. Okay, and then this simplifies to, okay, so this is 2 divided by pi is the same as the lim sub. Yeah, a to n divided by 2n factorial. And then the corresponding root. I actually don't have to take absolute value. Okay, so now one can actually deduce that this lim sub, that you don't have to use a lim sub, you can just use a usual limit. The reason for that is that the sequence an, this is strictly increasing. this is actually easy to see because it's this counting problem on the number of up-down permutations. And it's clear that the more letters you have, the more up-down permutations you have. You can, for example, see this from the recursion formula. It's also clear from this construction where we chop up-down permutation into pieces. So it's clear that this is monotonously increasing. So no worries about the lim sub. So as a result, I get that pi divided by 2, now I'm inverting everything, is the same as the limit for n goes to infinity of 2n factorial divided by a to n. And then I take the 2nth root of this. And now multiply everything by 2. I mean, this is easy enough. So this is twice the limit of n goes to infinity of 2n factorial divided by a to n, and then take the 2nth root. Et voila, there you go. So this formula is, however, a little bit different from the formula I had shown you at the beginning, right? This was the formula I had shown you at the beginning. This is a tiny bit different, right? You see that this fraction here is exactly the same as this fraction up here. You have also this factor times 2, but then there's an additional factor 2 here, and then here you take a different root than you take here. Now actually there's very good reasons to prefer this formula which I've shown to you, because this reasonably quickly gets close to pi, whereas this formula, even though this does converge to pi, it does so much slower, and this is not such a good formula. I mean, it does give you pi, but it just takes, it's not impressive if you try to compute many terms. You're not getting anywhere near pi, whereas this really shows you some good digits. So now we'll develop the formula for pi, which I showed you at the beginning. So again, we start with 1 divided by cosine over z, and we know that this is the same as the sum from 0 to infinity of a to n times z to the 2n divided by 2n factorial. Now, what we'll do this time is that I'll write the left-hand side as a partial fraction decomposition. So first of all, for this we need to know what the poles look like, but this is very easy because let's just look at the zeros of the cosine function. I mean, the cosine just looks like this, doesn't it? And it's periodic. And so we know, right, so here is 2 pi, here is pi, here is pi divided by 2, and here is minus pi divided by 2. So of course, this graph, this is just the real graph of the cosine, but this still reflects the behavior of all the zeros of the cosine, even in the complex plane, because all the zeros of the complex cosine are on the real axis at precisely these locations, where these zeros are here. Okay, so this means that the poles of 1 divided by cosine also will all be on the real axis, and they will be exactly at the zeros of the cosine function. Moreover, the orders of all the poles of this will be exactly the orders, or the inverse of the orders, of the zeros of the cosine function, but all of the zeros of the cosine have order 1. So this means that the partial fraction decomposition of 1 divided by the cosine will just be an infinite sum, because there are infinitely many poles. But since all these poles are of order 1, it will be an infinite sum of the term, like some constants, divided by z minus, and then w, where w is the location of the pole. Yeah, so it will be an infinite sum of such terms for possibly changing, right? I mean, so possibly changing coefficients. These might depend on the pole, and then w will run through all the poles. Good. Now, if I write this function as a sum of these, then I can say something about the numbers a to n, because I can also then expand the function, this function here. I can also expand this as a power series around the origin, get a corresponding decomposition expansion in this shape. And in particular, from each such summand, I get a contribution to what sums up to these summands. And the main principle here is that the bigger the absolute value of w, so this means the farther out the pole in the complex plane, the smaller the contribution to this term. This can be very easily seen by just expanding this as a power series around the origin. For this, I just write it as a geometric series. So I'll just divide by w, so I get cw divided by w, 1 divided by z minus z divided by w minus 1. And I can write this as a geometric series, right? This is minus cw divided by w 1 divided by 1 minus z divided by w, and this is the same as minus cw divided by w of the infinite sum from n to 0 to infinity of, well, what's that? This is 1 divided by w to the n times z to the n. Okay, I've tacitly assumed that no pole is at 0, which is fine for our function, because if you plug in 0 for z, this is just 1, so there is no pole at 0. Okay, but so for all the poles of the cosine function, the partial fraction has this shape, and then when you expand it around the origin, it looks like this. So this means when I sum many of these terms, I always just get like some coefficient here and an exponential term. This is like a term which has exponential decay, right? N increases, and, well, I mean, whether this is exponentially growing or decreasing depends on the absolute value of w, but at any rate, so you see an exponential function here in the variable n. Good. So now you can imagine when I sum many of these terms, this just means that I get, for these coefficients, also a corresponding sum, all of which are like exponential functions. So let's just say that all our poles are outside the unit circle, which is the case for the poles of the cosine, right? Because pi divided by 2 is bigger than 1. So then really this thing here is this is really exponential decay. And so this means, like, for poles, the farther out they are in the complex plane, the faster the exponential decay. So this means the terms here which decay the slowest, which therefore are the terms which have the maximal contribution, are those corresponding to the poles which are the closest to the origin in here. Good. So this means that actually the entire, all the contributions from the partial fractions in this a to n, well, they will be dominated by the contributions which come from these two poles, because these are the poles corresponding to the zeros of the cosine closest to the origin. All other poles are further out. This means w will have a larger absolute value, and this means that the contribution to the coefficients in the power series expansion will decay faster. So this is not a dominating effect. This is like just like a second order effect. Good. So this means what I'll have to do is I'll just approximate the function 1 divided by cosine by just the partial fraction decomposition for these two terms, and I'll discard the rest. And I'll later explain to you how I can be more precise about, this discarding at the moment. I'll later tell you why this is not a problem for our determination of the limit. But at the moment, the idea is let's just focus on the partial fractions which correspond to these two terms. So what are these? Well, I need to figure out what the values w are, which I already know is pi divided by 2 and minus pi divided by 2, and I need to figure out what these coefficients are. But this is not difficult, because these are, of course, just the residues of the function 1 divided by cosine at these 2 points, right? But this is just the -1 coefficient at the local Laurent series expansion. Good. So let's figure out what the residues are for these two poles. I can just use the standard formula. So I'll start with pi divided by 2. So I just have to take the limit. Z goes to pi divided by 2. Then I multiply, as always, with a 0, which has exactly the same order to compensate for the pole. And then I multiply with a function, 1 divided by cosine of z. Okay, and now this term here goes to 0 as z approaches pi divided by 2, and this term, the denominator as well, because this is a 0 of the cosine function. So I can use L'Hopital's rule. So I take the derivative, I'm going to write this as a fraction. So I take the derivative of this, which is 1, and then I take the derivative of cosine, which is minus sine. And now I can actually already plug in pi divided by 2, because the sign at pi divided by 2 is non-zero. Let's actually you can completely see what it is in a little graph. I'll just very quickly draw the sine function. So this looks like this. So here is 2 pi. Here is pi, so pi half is exactly here. This is +1, right? So sine of pi half is +1, so I have a minus here, so this is -1. Good. And now the determination of the residue for the pole at minus pi half is exactly the same computation. So z goes to minus pi divided by 2 this time, so the z plus pi divided by 2, 1 over the cosine of z. And everything is exactly the same, minus sign, but now this time I have to plug in minus pi divided by 2, which I can also quickly just evaluate from this little picture, right? We have minus pi here, so minus pi half is here, so this has value minus 1. Yeah, so I have a minus and a minus, so this is plus 1. So I deduce from this that the partial fractions corresponding to these two poles, they have the shape. Now for the pole at pi divided by 2, the residue was minus 1, and right, so this was minus 1. And for the pole at z plus p, so then for the pole at z plus pi divided by 2, so this is the pole at a minus pi divided by 2, the residue was 1. Okay, cool. So I know that the cosine 1 divided by the cosine of z is approximately this, plus partial fractions which corresponds to poles further out, but I already know that their contribution to the coefficients in the expansion around the origin will be smaller than these. So these two partial fractions are the dominating effect. Okay, so now I'll just need to simplify this. I'll just let's just find a common denominator. This is easy. I just have to multiply this, the first term, with z plus pi divided by 2, and this second term by this denominator. So this is minus z plus pi divided by 2 divided by z minus pi divided by 2. I'll already write this on one fraction. So, and then the other is z plus pi divided by 2. Okay, and here for the second term, this is, I just have to multiply with this. So this is plus z minus pi divided by 2. Okay, so I directly see some cancellation up here, right? So I have a z plus z and a minus z, and then I have a pi divided by 2, and, oh no, I have a minus pi divided by 2, and another minus pi divided by 2, so this is minus pi. Okay, so this is minus pi divided by, and this thing down here, this is z squared minus pi divided by 2 squared, third binomial formula. Okay, I'll actually get rid of the minus up here by just swapping the order of the terms. So this is just pi times pi divided by 2 squared minus z squared. Okay, now I recognize the shape of a geometric series. I just have to divide out by this pi half squared. So this is the same as pi divided by 2 squared times 1 minus z divided by well, pi half squared. Okay, and this is a geometric series, so I get, okay, let's simplify this a little bit. So this is, I'll just do this slowly. So this is pi divided by pi squared times 2 to the power 2. And then I have a sum n from 0 to infinity of z to the 2n times 2 to the 2n divided by pi to the 2n. Okay. This pi cancels against this term. So all in all, I get a sum from 0 to infinity of, and now the inner term is, well, I basically see a 2 to the 2n plus 2 divided by pi to the 2n, and then I have an additional pi here, so 2n plus 1 times z to the 2n. And does this seem all right? So I have a 2, this is here, so these two are here. I have 1 pi left, this is down here. Yeah, this seems all right. Okay, good. And now note that when I look at the original function, this was not just the plane generating function, but I also had this additional factor divided by 2n factorial. So let's artificially bring this into this formula. So I get the sum from 0 to infinity of 2 to the 2n plus 2 times 2n factorial divided by pi to the 2n plus 1 times z to the 2n divided by 2n factorial. Good. And so now the whole idea behind this is, of course, that I now know what the nth coefficient is in this function up here, which approximates 1 divided by the cosine. But I also know that this is the corresponding coefficient in front of z to the 2n divided by 2n factorial. This is just a to n. So I know that a to n is basically approximately this term. Why only approximately? Well, because I've made this approximation up here, right? So, but very quickly I can deduce from this that a to n is approximately the same as this coefficient, which is 2 to the 2n plus 2, 2n factorial divided by pi to the 2n plus 1. So let us actually check how good this formula is, which is very easy because I still have this program which can actually count how many up-down permutations there are on 2n letters. And I can just compare this to the value which our little formula gives us. So for example, in the case of the up-down permutations on 4 letters, I get the actual count of 5 and the formula gives us 5.01. And well, let's just do it on 6 letters. Okay, so here you see the list of the up-down permutations. There are 61 and our formula gives us 61.02. So it's actually pretty good. Now, actually I wanted to give you a proof for why you can use this to compute pi. So it's not so good that I only have an approximation here, right? I need something more precise. But this is not really a problem. So let me just quickly explain why this is good enough here and how to get rid of this approximation sign. So the whole story was hidden in here, right? I had just replaced 1 divided by cosine by a partial fraction, but then I omitted all the other partial fractions which correspond to poles which are further out. But I'd already explained to you that the contribution which comes from these poles further out, that this decays, that this has exponential decay, but it decays even faster. So what does this mean about these coefficients here? Well, I'll just do this on a different sheet of paper and just in a rough shape. So let's for a moment just ignore this term 2n factorial, right? So I just have a term here and this is basically exponential in n, as you see. So what I've deduced just from these two summands here is something like a big factor, let's call it alpha times, I can write 2n or n. Well, let me just write 2n. Okay, so yeah, so this is just like in my, I'll just explain the pattern of the computation. So this alpha to the 2n, this is basically this, a big fat term without the 2n factorial of exponential type. Good, and now I know that for all the other partial fractions which I omitted here, right? There would be many more, right? There would be many more unknown coefficients divided by z, minus, and then here the locations of all the other poles, the poles which are farther out. Okay, and so all these also contribute, as you see in this formula. Also all these other summands, they all contribute a term with this exponential type, but this time the absolute value of w is bigger, so this decays off faster. So this means really, instead of just this term, if I add all these, there's more of these, right? If I add all these further terms, then I get more summands here, and they are all of exponential type. So I'll just call them epsilon naught, 2n plus epsilon 1, 2n plus epsilon 2, 2n, corresponding to all the other partial fractions, whatever. And, they might also have some interesting coefficients, whatever, corresponding to these. This can all be computed, but we don't need it. So there might be some additional coefficients, whatever. I call them C tilde 0, C1 tilde, C2 tilde. Okay, good. But of course, I can always rewrite this expression as alpha to the 2n times 1 plus, and then the first coefficients time epsilon 0 divided by alpha to the 2n plus c tilde 1 times epsilon 1 divided by alpha to the 2n plus, and so on. Right? This is, I've just rewritten the term. But the other thing is, all the other poles, they are farther out in the complex plane. So this means, as I explained, that this W is actually bigger, and this means that all these epsilon, right? So this W, it occurs in the denominator, so the W is bigger in the denominator. So if I write this as a numerator, it means that the 1 divided by W gets smaller. So it means that all these contributions from these epsilon terms, they are all smaller than the alpha. So this means that all these factors have absolute values smaller than 1. Okay, and this means as n goes off to infinity, basically all these terms here converge to 0, which means that the entire factor here will converge to 1. And this means that in our little formula, in our little computation here, where we will determine this formula, if I add all the other partial fractions, all that happens is that I would get an additional factor in here of this shape, which, however, as n goes to infinity, converges to 1. Now, I'm sweeping a few details under the rug. So first of all, this is an infinite sum, which I didn't really invest any time thinking about. So you probably also need some control over what these coefficients are. This just corresponds to the residues of the cosine function. It's at the different poles. This is not difficult to compute. Anyway, but so this is the rough idea. So if you have more of these factors, you'll just get this thing here, and as n goes off to infinity, this contribution disappears. So this means that actually this approximation formula, a to n, is approximately the same thing as that thing. As n goes off to infinity, this actually, the actual error here is just an additional factor in here, which converges to 1 as n goes to infinity. So this means when I now resolve this for pi, which gives me pi 2n plus 1 is approximately the same as 2 to the 2n plus 2 times 2n factorial divided by a to n. Now there would also, like if you want to make it precise, there is now this additional factor which converges to 1 as n goes to infinity. Okay, now I take the 2nth root, and what do I get? I get pi is approximately the same. Okay, I'll just write this as 2 to the 2n plus 1 times 2 times 2n factorial divided by a to n. And now here I take the 2n plus first root. Right, so what I did here is that I just copied this term. I put the 2 in here to take the 2n plus first root, and here I haven't taken the 2n plus first root yet, but this just means that this power disappears. You see, I arrive exactly at the formula which I had shown you in the beginning. Pi is approximately 2 times 2 to the 2n factorial divided by a 2n, and then you take this 2n plus first root. And yeah, remember, so getting rid of this sign of approximation just means that here there's an additional factor which goes to 1 as n goes to infinity, and this factor just survives through the entire computation. Okay, and then it's maybe a bit delicate because you take a 2n plus first root of this factor, but if you care to look at the details, then it turns out that this still goes to 1 as you are in the limit n goes to infinity. And so this, I mean, I've presented this now as a slightly simplified computation with this approximation sign, but I hope the idea is clear. So in the end, you indeed get that pi is the same as the limit n goes to infinity 2 times 2 to the 2n factorial divided by a to n, and then the 2n plus first root. There you go. This is not the only way to prove this. I could also, instead of doing this whole approximation stuff, I could also just have used the full partial fraction decomposition, which is known. It's not so difficult to work out. I mean, basically, you just have to imitate what I did for these two poles. I mean, you can just do this computation for all the other poles. As you see, it's not really difficult. So when you do that, You can also work out the entire partial fraction decomposition. Okay, and then you just get everything in completely precisely, and you don't even have to worry about these approximation arguments. So that's another way to do it. Yeah, that's it.